Hi students, in this lecture we're going to go over Coulomb's law, and in particular we're going to talk about the scalar version of Coulomb's law. This should be a review from what you guys learned in 183, but it's nice to go back over it. We're going to define the terms in the same notation that your book uses. The associated reading, which you guys should definitely do, is the beginning of chapter 2. And again, in this lecture, the learning objectives is just to define the terms in Coulomb's law. All right, so let's review it. We're talking about Coulomb's law. And Coulomb's law is all about understanding, this by the way is the scalar version, which means we're only worried about the magnitude of the force between two charges. At this point, we're not going to talk about the vector direction, okay, of those forces. But Coulomb's law, it's all about understanding the electric force between 2 point charges. Point charges, right, just like a point mass, we're assuming all of the charge is concentrated at a single point. And in your book, one of these charges has a charge of little q. The other one is labeled as having a charge of big Q. And if these two charges are separated by some distance, let me write that a little straighter, okay, R, then Coulomb's law tells us that the magnitude of the force between them is going to be equal to, we'll use Ke for now, that's Coulomb's constant, times little q times big Q over R squared. I've got these magnitude notation and the absolute value here because, again, I'm just looking for the size of that force right now, not the direction. So I don't actually care about whether the charges are positive and negative. All right, so let's go over the terms here. First things first, Q in this equation, okay, that is, the little q is the charge of the source charge, what's called the source charge, okay? And this is kind of important vocabulary that you guys should remember. The source charge is the charge that is creating the electric field that we are trying to understand the force of, okay? So Q is this charge, it's creating electric field in space. We're putting this other charge in here to understand the force due to this source charge. It could also be more than one charge. We're going to deal with that pretty quickly, okay? But the little q in these equations in your book in the notation, those are source charges. In the beginning of this class, we're dealing with a portion of electromagnetic theory known as electrostatics, okay? And that static should mean something to you guys. In electrostatics, we're simplifying E&M theory by assuming that the source charges are stationary. Okay, they're not moving. And that makes things simpler because, as we know, electromagnetic fields don't instantaneously appear everywhere. They actually travel with some speed. So if the source charges are moving, that complicates how that electromagnetic field propagates through space. All right, so that's what little q is. The big Q is also a charge, but this is the charge of what we call the test charge. I don't know if you guys remember that PhET sim. Maybe I'll put a link to it on the page, the one that shows the electric field around a collection of charges. When you use that sim, you take a little sensor, which is like a test charge, and you put it in that electric field, and that sensor tells you what the electric force is in that electric field. Okay, so our test charge is kind of like that. It's a charge that I'm going to put in this electric field produced by Q, and the force that I'm measuring is the force that is on the test charge. Okay, so if the direction of the force is outward, right, that means that the force on this test charge is outward. Okay, we're not talking about the force on Q, little q, we're talking about the force on big Q when we're using Coulomb's law. Okay, in let's see, so I'm going to write that down. So the force is on this charge, okay? So that's important to remember, all right? In electrostatics, this charge can move. And in fact, we're often trying to understand how this charge would move in that electric field, okay? So Q can, well, I'll call that the test charge. Calvin, you're not helping. Can move. Okay. One other thing to kind of note about this test charge, it does have its own electric field, of course. It is a charged object, but that electric field, if this is positive, right, we got some electric field facing outward, that electric field does not exert a force on the test charge itself. It's in space. It could exert a force on another charge in reality, but we're trying to understand the force on big Q, and big Q's electric field doesn't exert a force on itself, so we don't have to worry about the electric field produced by our test charge, big Q. All right, so the only other thing we got in here that's not, well, R is the distance. That's kind of obvious, okay, between the charges. The other thing we got here is Ke. That is what's called Coulomb's constant, named after the guy that came up with it. Whoops, not Coulomb's law, Coulomb's constant. Okay, its value is about, it's a little bit less than this, 9 times 10 to the 9. If I look at the units there, I need something in newtons, so I need to have meters squared on the top to get rid of meters squared on the bottom of that equation. Oops. And coulombs squared on the bottom. That way my units work out. Okay, this is how introductory physics often deals with Coulomb's law. There's a little bit more mathematically meaningful constant that we're going to talk about in maybe the next lecture or 2 lectures, and that is related to this Coulomb constant. And Coulomb's constant is equal to 1 over 4 pi divided by, or 1 over 4 pi times epsilon naught. Epsilon naught is the constant you guys are going to be dealing with more often. It's the permittivity of free space. I'll talk about it in the next lecture.